Hey folks, welcome to Module 3 for the AI Accelerator for Product Quality Detection. I think first what we want to start off with is an overview of what this algorithm is technically doing. There were a couple of options on the table as far as what we could do. And fairly well documented is using what's called a neural autoencoder. And what you would essentially do to detect an anomaly using one of these is that you would train one of these autoencoders. You would take a sample from your live data feed, encode it and decode it, and see how well did it construct that decoding, how many deviations away from a normal error was it at encoding and decoding this particular sample. That's really, really cool and really wonderful, and gives you a lot of value if it can work. The issue that we encountered was that our data feed produces one anomaly for every 100, and our encoder network was a little bit too robust. And we can talk about that. These are some of the knobs that you have for turning. And if you're an internal solution versus an external solution, maybe you can turn some of these knobs a little bit differently. But the big issue was the complexity level of the neural network is able to understand and represent a significant amount of data fairly effectively, which means that the amount of samples that are allowed to be represented in your data set to be a true anomaly, if you're training with the anomalies in the data set, has to be really, really small. If you're an ISV, this is super, super challenging. So the encoder, decoder, and deviations away from normality is probably one of the more challenging and difficult approaches to take, unless what you have truly, truly is an anomaly. And to define anomaly is going to require some research, quite frankly. It has to be a really small percentage. 1 in 100 just wasn't small enough. I really honestly don't think 1 in 1,000 would be small enough. I think you're talking probably more like 1 in 100,000. But again, to actually validate that percentage, we'd have to do some real tests and validation here. So what ended up working fairly effectively, and the algorithm that we have in place, is to train an encoder decoder, so an autoencoder like you typically would for this type of anomaly detection with deviations. But then what we did was we threw the decoder away and we encoded the entire data set and then fed that into a k-means classifier with 2 clusters. So again, knobs for turning are how many clusters do I have? This is kind of an important concept. So if the anomalies are a little bit more occurring in your data set, that might mean that they're not actually necessarily quote unquote anomalous. They're possibly just issues that are well represented. And it would behoove you to understand how many types of issues so that you know how many clusters to try to create. In the simulated data set, I have an anomaly that has one very specific pattern, and I have a non-anomaly which has a very different specific pattern. So defining 2 clusters was a very good no-brainer. Also, the memory capacity of my network had to be fairly robust because there was a lot of random variables being generated. There wasn't a lot of consistency in a sample that was created to the next sample that was created because of the wide array of randomness that was allowed to happen. So that meant that I needed a fairly robust neural representation to create the encoding. And I also knew how many clusters I had. So those are big distinct advantages when I have curated my sample. This is going to be more analogous to somebody who's building an internal solution. You can hand tweak those things for yourself. In the case of an ISV building one of these, you're going to have to build those knobs into your solution to allow somebody like an industrial engineer to play with those knobs and see what kind of results they can get and cross-reference that with factory statistics. So high level, that's the type of algorithm. The code is broken up into two parts. We have an explore, which the explore file really is the training of the neural autoencoder. And then we have a clustering file. Now, I will be building a train model.py, and that's just going to combine both steps into one. But I thought I would review the two separated so that you can see some of the Wild West that sometimes happens in the data science and exploratory process, and how some of the tools actually help enable that, and what the process would have to look like to take that Wild West, wrap it up, put a bow on it, and automate it. So here we're looking at the quote-unquote explore portion of the process, where I ended up actually training several autoencoders. So the first thing is to mount the data storage facility. So remember that Stream Analytics is dumping into Azure Blob Storage. Should be Data Lake Gen 2, but looks like we're missing the connector for that at the moment. So Databricks supports both, so we went with this one because it works. So anyways, this first section of code mounts that onto the Databricks cluster. This simply just discovers all of the files and appends them to a big list. It's not Avro files. I know it says Avro. Started off down the Avro route. There was issues with that. JSON is a much, much happier format. Go JSON. So what this block of code does is it actually reads every data file that is in the data lake, and then builds a massive distributed data frame. And this is where some of the wonders of Spark and Databricks come to bear, is that I can get all of that into memory and start to do computation on it. In fact, let's see here, that's so 1.7 million rows in that data frame. So it's a fairly sizable kind of thing. This block of code is just going to give us a view of what that data looks like. What's important to note here is that Stream Analytics was doing the transformation from a raw feed into a more generic format. That genericizing of the data is going to allow us to do things like in the next couple of blocks of code where we figure out, hey, what are the variables for telemetry, right? Is it ambient humidity? Is it temperature? Is it voltage? Is it flux capacitance, right? Like it takes and figures out what are the keys inside of the telemetry section of the data frame and allows us to start working with that. Same thing with the features, does the exact same thing with the features. Here what we do is, now that we know what the unique features are, we need to know what the scope, what is the entire environment, how many unique types of things are in there. And this is used for one-hot encoding, which is actually next. So this next set of code, what this is really doing is this section, lines 3 through 15 that's currently highlighted. This takes the telemetry, which was one of the key, like the required forms in the genericized format, and the list of telemetry keys, and it creates a time-based matrix for machine learning. So machine learning is nothing more really than super fancy linear algebra where we're multiplying matrices by other matrices. So at the end of the day, you need a matrix. So what this does is it figures out, okay, how many time steps are in there? How many keys are in each time step? You know, it's a multivariable type solution. How many variables? build out an empty matrix of that size and fill it up. That's pretty much all it's doing. What this is doing is it's figuring out what the domain of my categorical features are, and it fills up a vector with an encoding. So what one-hot does is basically say there's a feature and it has a world of 5 possibilities. It'll have 5 different zeros, and you're going to stick a 1 for the thing. So if it's silver, gold, plastic, I don't know, stone and glass, and it was stone, you're going to put a 1 here and a 0 everywhere else. So that's what that does. This code here basically converts it into a user-defined function that can then be applied on a distributed data frame. This code actually goes ahead and applies it and creates new columns out of it. So when we do the one-hot of the featureization, we're going to create a new column called hot feature. When we create the machine learning compatible matrix for matrix multiplication for the telemetry, we're just calling that telemetry matrix. That's all it really does. This is just some testing, so you'll probably see if it hasn't been automated yet and it's in one of these kind of notebooks, there's a lot of exploratory code. I highly recommend trying to get stuff out of exploratory code and into something that can be automated. This particular notebook, no way. I don't think this could be automated. If it could be automated, it's going to be a pain in the butt to maintain. Now we're pretty much ready to do some machine learning. We're going to use Keras, and there's a reason here for Keras. So let's take just a step back and talk about that, because folks will probably say ML Flow or Spark ML or whatever distributed machine learning framework of your flavor of today that you want to pick. The thing about the distributed machine learning frameworks is that they require a Spark context. And because they require a Spark context, they're already heavyweight. That means that you have to have Spark installed and running and ready to go. It's harder to put that in your landing zone. So yes, it may be easier to train a distributed, train a neural network or an algorithm on a distributed compute cluster, but when it comes time to actually operationalizing that, which is where the real value is, right? Like the value isn't in training that, value is in using what I've trained. It becomes challenging to take that and put it into production. Keras is a little bit lighter weight. I don't need Spark. I don't need a Spark context, and I can run it in a variety of places on some fairly small scale compute capability. So what I decided to do, instead of using like a Spark ML and then trying to figure out how do I get that to run inside of these smaller areas, was how do I create a bridge between a machine learning capability like Keras and train it with distributed data frames in a Spark environment. And that's where this set of code comes. So what we have here is a Spark RDD data generator. What this essentially does is you give it a Spark, when you instantiate one of these, you give it the Spark data frame that it needs to slice up, how big your batches are going to be, what your X column name is, and what your Y column name is. So that's what this kind of does. And it adheres to the Keras data generator interface. There are some caveats to this. Typically, if you adhere to this interface, you get to take advantage of the multi-worker capabilities. Spark, at least at the moment, doesn't seem to be able to pickle an RDD. So understandably so. So there's a couple of small issues here. So you're kind of stuck on single worker against a massive data set. That just means that train time is going to take a little longer until the multi-worker problem is resolved, which means figuring out how to not have to pickle an RDD. Don't worry about that. What it ends up doing is saying, hey, this is how many batches make up an epoch. So a single epoch is an entire pass through the data set. How many batches make up an entire pass through the data set? Get item is actually returning a batch to be trained on. So this goes and grabs whatever from the X named X column. So batch.select from the X defined X column and the Y column, and it returns those back in the correct format for machine learning for training. In this case, we're using an LSTM autoencoder. We wanted to make sure we respect the time domain. So that has to be reshaped into a particular format for an LSTM. So there's a little bit of inner knowledge as to what kind of algorithm I'm training required in constructing this. But this is a really great kind of generator to start with, and you could get some good use. Now, if I could fit all of the data onto a single node, this thing is totally useless. I wouldn't use it. But if I truly do have a super large data set, this is the way to go, and this will allow you to train on that large data set. Defining the model. So here we can see a couple of different attempts. This one, I don't remember what was the issue. This one trained well. What ended up being was that we needed to split the model into an encoder decoder. So in this example, this is what you'll typically see in Keras as an example of how to build an autoencoder. It's great. It's an autoencoder. It does exactly what it's supposed to do. The problem is, in using the autoencoder, this is a single model. It's called model. I can't split it into two parts. What this one is, this is an autoencoder split into the encoder and the decoder. That means that we can separately load and use the encoder from the decoder. If we go back to the example of what our algorithm looks like, if it's paired together, the output looks like the input. I can't feed that to a k-means. The reason I want to encode and create an encoded representation is that a three-dimensional matrix isn't really something I can feed to k-means. So the encoded representation, however, is something that I can. So what we're doing is we're using the neural network's natural ability to condense and featureize, and then we feed its understanding of those features into k-means. And we know it does a good job because it can encode to that slice, that small slice, and it can effectively reconstruct the entire input from that. That means it learned the most important combinations of things. Those series of numbers are not anywhere close to human understandable. I don't even know if I had a PhD if I could figure it out. It's better to just understand that it's an optimization problem, and it found the optimal paths and the optimal matrices to multiply by, and that yields that vector. And in our case, our vector has 30 values to it. So we take the entire time sequence, and we encode and decode, and we learn a condensed representation of 30 floats. And we can decode that. And we can see that the loss is error. We can see that the loss is improving. So when we first go through our first epoch, 5,309. It's terrible. But look, the next one, 3,312, 2,100, 1,600, until we get down to 808. It probably could have kept going, but I needed to just try it. It actually works fairly effectively without letting it keep going. So what we end up doing here now is we are trying it out a bit, but more importantly is this code. We're going to write the models, the encoder and the decoder, to the temp folder for models anomaly. Then remember in our architecture diagram we had the model zoo. That was our mechanism for transferring models around. We're using the Azure Machine Learning Service, and here we're actually using dbutil secret, so cool. This is the way you should be doing this because it will work same code across multiple environments between dev, QA, integration, prod, so forth and so on. Anyways, we use the Acc Ml workspace and model repository. So we use a service principal authentication because we can't do interactive authentication in a distributed cluster. So step one, make sure you have a service principal. We find our workspace that we've created, and then we register this model. And note the model name, anomaly encode decode. We give it a version number and a state. This, when it executes, stores that into the Azure Machine Learning Services as a model. So here we have the second notebook, which is part 2, where we do more of the experimentation around the two algorithm choices, whether we encode, decode, and calculate between standard deviations, or if we just encode and use a k-means. So again, first step is check to see if we're mounted to the data store. If we are, great, move on. If not, go ahead and mount. Here what we do, because it's a separate notebook, we're going to go ahead and load the model and download it somewhere just to make sure we have the model that we had in the previous step. So again, service principal authentication, register with a workspace, the model, anomaly, encode, decode, the specific version that we trained in the previous step. And then we're going to make some directories and download all the files there. Yep, so here we go, encoder load model, no train configuration found. Really doesn't matter because we want to use the end result. We're not trying to resume training. So we load the encoder and the decoder. We load up all the JSON files. Compose those into a massive data frame. Do the same thing that we did before. We got ambient humidity, temperature, amperage, capacitance, voltage, factory ID, line ID, unique factories, unique lines. So everything's kind of working the way it's supposed to. Telemetry to matrix, one hot features, all that transformation. Here's actually the output for you. So you can see that the feed that we're expecting is features, meta, and telemetry. And it added the hot feature and the telemetry matrix. Now notice the hot feature is a composition of Seattle and line 3. So if it was, 0, 1, 2, 3, 0, 1, 2. So we should see 3 and 2. So 0, 1, 2, 3 has a 1, 0, 1, 2. There you go. So one hot feature, that's how that works. JSON for the telemetry, check it out. List, that's what it looks like, 47, 1, 27, 92, 75. When you compose it in order, 47, 1, 27, 9, 75. But it's a matrix or an array. So, the conversion to UDF, go ahead and show what that looks like. Now we have everything that we need. Again, we get the Spark generator. This is just a really easy way to extract to. You can use it as your own thing. So I want to go ahead and sample 10%, and then I'm going to go ahead and create a generator off of 10% just to make things move quickly and get an even smaller batch. I just want 10 things out of that. I happen to know what an anomalous shape looks like. I have a sample set of those, so I went and generated a few of them, copy and pasted the values. X_A means anomaly, and this is the first one. So it's got 10 time steps and 5 variables. That's the first. Oh, I forgot what that was. Oh, that was testing out some summing stuff. So again, this can be a bit of a challenge when dealing with code directly from science people. I'm guilty of this, and all get out is that, hey, look, I'm going to just try experimenting here, and then I'm going to go up here and experiment here, and then I'm going to go down here and experiment here. We're all kind of guilty of that. So it's important to do the wrap-up step afterwards. So the train model, where you just go through the cohesive thing that can be automated, because again, chances of this being automated or somebody else being able to step in and do it, pretty low, because they're going to look at that and go, huh, why is he doing that? I'm actually just checking something to see if it was what I wanted to do for probably a reshape. So check this out. This is interesting. So y-hat, the prediction, decoder.predict. Remember, we had an encoder and a decoder. The decoder, so we're going to print y-hat, is the same size as the input. So this is a 10 by 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 time steps, and 5 variables within that time step long. The error matrix that we got, the average for the error that we got, and the sum of the total error that we got. So if we go ahead and do the same thing, we get some deviations. This is where things start to get interesting. So the next set is going through experimenting. What's an average error look like across just the whole data set? What's the standard deviation? And what are the values? What are my windows? 1 deviation, 2 deviations, and 3 deviations away from mean. That's your typical anomaly detection. If I'm more than 3 deviations if I'm outside of the 3 deviation window, well, that's definitely an anomaly. That's kind of your canonical example. So for encode and decode, if my decoded error is more than 3 deviations away, it's an error. This is going to lead to a lot of false positives in this case. I mean, check this out. So we took the anomaly. It was 1169. That's within the 1 deviation window. So, you know, like I said earlier, this is a result of having a robust enough network to try to capture and encode and decode the data set and have low error in a fairly crazy looking data set. And the fact that the anomalies are actually not huge anomalies, like it's not 1 in a million kind of thing. In this case, it's 1 in 100. So it's very well represented, and you can see that because it's falling within the 1 deviation. So we really had to change our strategy here, and that's where k-means was coming in. So, and this is where one-year knobs is, right? Number of clusters. I have good and I have bad, right? So I have 2 clusters. So what we did instead was we took a mini batch. We didn't train on the whole thing, but we took a mini batch of stuff and encoded that. That then became our features. These are now a mini batch. Let's say, I can't remember how big our mini batch was, but that would be, say, 1,000 samples. And when we encode that, each of the samples now has 30 values with it. We train a k-means on that with 2 clusters, and we fit it on the features. So now when we actually do an encoding, you'll see here, we're going to get the normal one, which is grabbing one of the ones that I verified was normal. And we're going to get so x_in is a normal one. x_in_f is the features from the normal one, because we use the encoder. It's very important. Now, x_a_1_f is the features for the anomaly. So we predict on the anomaly. print the shape out. So it's one sample with 30 features with it. Let's go ahead and predict using the clustering algorithm we trained before. 0 and 1, so they're separated into two clusters. Important thing to know here is that we don't necessarily know which cluster is the anomalous cluster and which cluster is the normal cluster. However, it can be assumed that the cluster with the most examples in it is your normal cluster, and the other clusters are your anomalous clusters. And that's how we got the algorithm. So this is effectively training and giving us results and separating them into two separate buckets on a fairly complex data feed. I mean, let's go look at this thing. I mean, the data looks like this. It's time sequences. So, you got this over 10 time steps with some factory metadata, and it can detect a pattern over that time window because we respect and use a time-oriented encoder. This is some powerful stuff. To be able to just take that and be able to separate it into, distinct buckets. So that's pretty cool. So the last step is to start persisting and saving all the files that we need so that we can use those in our inference function. So we go ahead and we create a temporary folder for models and anomaly. We make the directory. There are a couple of key things that we need. We need the clustering model. We need the anomaly definition. So in this case, if we go look, normal was the 0 cluster and anomaly was the 1 cluster. So anomaly is the 1 cluster and normal was the 0 cluster. So I want to make sure that I persist a mapping so that inference knows, oh, it predicted a 0. Great, what does that mean, right? Need to be able to reverse the transformation into something that your average Joe can understand. The telemetry keys and the feature keys and the unique features, those all need to be persisted because you can't be extracting that from a single sample. When you are looking at the live data stream, you're not composing this huge distributed data frame of all the universe and then extracting and calculating that. Like you just don't have the time or memory to do that in that location. So we're going to go ahead and persist those because they're key for our transformations. We then go ahead and just save the encoder and the decoder in the same folder, and using the same Azure machine learning model registration capabilities in the workspace, we register that model to the anomaly encoder decoder. This is 1.0.0.4, and it's a dev candidate. We can now use this wherever we want. We can generate Docker containers from this. We can stick it into an Azure function. In this case, with this sample, we're going to put it in an Azure function. So at this point, we are concluding the third module, which is the machine learning oriented module. Again, like anything, feel free to ask questions, pose questions in the issues in GitHub, and hopefully this has been useful. And thank you very much, and hopefully you look forward to the next set of modules.